Look around the room you're sitting in right now. Inside your phone, there's a network of copper wiring. The laptop on your desk is likely encased in aluminum. That pencil nearby holds a core of graphite, and every breath you take pulls in oxygen. Every single physical object you interact with is constructed from elements belonging to one of two massive categories: metals and nonmetals. You probably picture metals as heavy, rigid blocks, and nonmetals as invisible gases or brittle powders. But the reality is much stranger, and the exceptions to these basic classifications dictate how our technology actually functions. The devices we rely on daily operate under strict invisible elemental constraints. By testing these boundaries, we find materials that do exactly what they aren't supposed to do. Take the rule that all metals are solid at room temperature. Mercury breaks that assumption immediately. It's a dense, silvery metal that flows completely as a liquid, pooling and dividing without ever solidifying under normal conditions. Conversely, we tend to assume nonmetals are dull and matte, yet iodine, a nonmetal, forms sharp crystals that reflect light with a brilliant metallic shine. The true defining traits of metals happen down at the atomic level. Take malleability. When hammered, a metal's atoms slide past one another in sheets. The bonds hold, allowing it to flatten into foil. This internal flexibility also allows for ductility. Pulled from opposite ends, layers rearrange, stretching the metal into a continuous wire. Nonmetals lack this atomic flexibility. Apply that same physical pressure to sulfur or coal, and the rigid bonds instantly snap. The material shatters into a powder. Knowing exactly where these physical limits lie and isolating the rare elements that ignore them gives engineers the ability to shape raw earth into complex modern machinery. This internal structure also dictates how energy moves. Inside a metal, the arrangement of electrons creates a wide-open multi-lane highway. Electricity and heat can race through the material with almost zero resistance. Nonmetals trap their electrons tightly. Attempting to push an electric current through them is like driving a sports car down a rocky dirt road. They block the flow entirely, making them excellent insulators for wrapping live electrical wires. But again, there is a massive exception: graphite. Graphite is a form of carbon, making it completely nonmetallic. Yet, if you hook a standard battery and a small light bulb up to a piece of pencil lead, the bulb will glow brightly. The graphite carries the current just as effectively as a standard copper wire. A material's ability to conduct energy relies heavily on the specific geometric arrangement of its atoms, allowing certain nonmetals to perform tasks typically reserved for metals. When it comes to bearing heavy physical loads, iron is the primary element we rely on. Its incredible tensile strength forms the skeleton of modern bridges, buildings, and railways. But iron has a severe chemical vulnerability. If you expose it to dry oxygen, very little happens. Introduce moisture into that mix, however, and you trigger an aggressive chemical reaction. The iron atoms bind with the oxygen in water to form iron oxide, commonly known as rust. This new compound is brittle and flaky. As it expands and falls away, it exposes a fresh layer of iron underneath, allowing the cycle of destruction to continue until the metal is eaten through. We can test the chemical nature of these reactions using litmus paper, a strip that changes color to measure acidity. When metal oxides dissolve in water, they create basic solutions that turn red litmus paper blue. Nonmetal oxides do the exact opposite, forming acids that turn blue litmus paper red. Some metals will naturally resist this decay. Pure gold does not react with oxygen or water at all. We can also engineer this resistance by mixing iron with elements like chromium to create stainless steel, forming an invisible, self-repairing shield over the surface. Every structural design must account for this chemical vulnerability. The environment's impact on a material dictates its lifespan, turning corrosion into a ticking clock that engineers must constantly fight to reset. If pure gold is an excellent conductor of electricity and is entirely immune to rusting, why are our global power grids wired with copper? Copper is slightly more reactive and a slightly worse conductor than gold, but it is vastly more abundant in the Earth's crust. Wiring thousands of miles of infrastructure requires an enormous volume of material. Every decision in industrial design is a calculated compromise. We weigh a material's absolute chemical perfection against how much of it we can actually pull out of the ground. We leverage nonmetals for highly specific tasks based on their reactivity. The heads of standard matches rely on sulfur and phosphorus. These non-metallic elements ignite rapidly under friction, allowing us to harness a controlled burst of fire on demand. To protect our heavier infrastructure, we deploy zinc coatings and complex alloys to shield vulnerable iron. The iron pillar of Delhi has stood exposed to the elements for over 1,600 years, yet it shows almost no signs of rust due to the mastery of early metallurgists. By understanding the precise ways metals and nonmetals interact with heat, electricity, and moisture, we engineer structures and devices that survive longer in harsh environments, reducing global waste. The periodic table serves as an inventory of the physical universe. By knowing exactly when to follow its rules and when to exploit the elements that break them, we gain the exact toolkit needed to build a resilient, sustainable world.